Here we are preparing for our limits and continuity test, and we've had an assignment which is essentially just a sample version of our upcoming test. So our test is going to have this format, and I wanted to run through solutions to all the problems and hopefully give you some idea of what to expect when you take this quiz or this test in a few days. So we're going to begin with some limit problems. These are all multiple choice. And essentially, these are just substitution problems, just to get you warmed up and build your confidence up. You guys have been working hard on these things, and you're very good at a lot of this stuff. So I want to give you credit for that, and then hopefully build towards having you solve some more challenging problems. So we'll dive right in, and on this first problem, we're just going to use substitution. So we're just going to do 1 plus 5, and that answers 6, so we're going to choose letter B. And that one's that easy, and it's going to feel like that for a while. You always try substitution first when you're doing limits, so just remember to keep trying that. So we're going to try it until it stops working. In this problem, I'm going to plug 3 in, so I'm going to have the cube root of negative 2 times 3 minus 1, right? And negative 2 times 3 is negative 6 minus 1 is negative 7, so that's letter D. And we're cruising right along. I'm feeling better now. I'm getting some right answers. Oh no, I come to some trig. Now you do kind of have to have a clue about the unit circle to get this problem right. So what we're going to do is put 2 pi in there. When you do 2 times 2 pi, you get pi. So essentially we're just trying to compute the sine of pi times 2. And the sine of pi is 0, and 2 times 0 is 0, so this is letter B. If you are having trouble with your unit circle, then this problem is going to be challenging. There's no way to avoid it, but everybody should be pretty comfortable putting 0 for the sine of pi. Moving on to number 4, we've got a polynomial. We know this limit exists, so we're just going to plug it in here. We're going to have negative 8 plus 16, which is 8, minus 7, which is 1, and I get letter C. So all in all, I'm starting to build some confidence. I'm thinking, man, Mr. Murphy made this test way too easy. And then we get to number 5, and I'm going to plug in a 2. So on top, I get 2 minus 2, which is 0. And on the bottom, I get 4 minus 10, 12, plus 8. And that is also 0. So this is the first time that we've actually gotten an indeterminate form. And you know I love to do math when I get an indeterminate form. The strategy for this one, because it's a rational function, is that we're going to factor the bottom and see if that 0 cancels out. So we still have x minus 2 on top, and on bottom this factors to x minus 2 and x minus 4. And sure enough, we do have a hole in this function. The limit is going to exist. These cancel, and I get 1 over x minus 4. When I plug in 2, that is going to be a negative 1/2. Which doesn't seem to be one of the choices. So what went wrong here? Aha, I see what happened. I missed this negative sign right here. So when I cancel out the, oops, that shouldn't be yellow, that should be red. When I cancel out the x minus 2's, there should be a negative sign on top, and then there's also a negative on bottom. So this makes positive 1/2. Whew. I thought I made a mistake there. Well, I did. I thought I made a mistake on the answer key. The answer's right. It's A, 1/2. Please be careful and pay attention to these negative signs. Notice there's another one right here that we'll pay attention to when we do this problem. So let's wrap this slide up by finishing off this one. Maybe I'll get through here without making a huge mistake. There's a negative sign there. I got the x plus 1. I put a negative 1. That's a 0. I put a negative 1 on the bottom. I guess I didn't need to write this out. That's going to be 1 minus 3 plus 2, which is also 0. Indeterminate form. We'll factor the bottom, which is x plus 1, x plus 2. These guys cancel. I have a negative 1 on top. Don't forget that. And so this is going to be negative 1 over 1, which is negative 1. So we got letter A again. Okay, the first 4, straight up substitution. The next 2, factoring and canceling because we have indeterminate forms. When you take the real test, it's going to have the same format. So you'll be confident at least knowing that this is how the progression is going to go. It'll still be your job to perform and to get the right limits, but I don't want there to be any surprises for you. Let's move on. We are also going to do limits on some piecewise functions, so we're going to pay attention to the left and right hand limit notation and make sure we're coming from the correct direction. So you can see here that x is going at 0 from the left. That's what that little negative sign right there means. It means left. And in this case, we have to pick the rule that goes with numbers that are less than 0. And so that's this rule. So I'm going to do direct substitution on that guy, and that'll be the value of this limit. So that's just going to be 0 plus 1, which is 1. So letter D, answer is 1. I chose the top expression because I'm coming at 0 from the left, meaning I'm going to be less than 0 when I'm coming at 0, and so I have to use the rule that's for less than 0. Okay. On number 8, I'm also coming at 2 from the left. So again, I'm going to choose this top rule for this function, and I'll do direct substitution there. That means I'm going to plug a 2 in, so that's a negative 1 minus 1/2, which is negative 3/2, which is letter B here. On number 9, I'm coming at 0 from the right side, the positive side. So that means I'm going to use this rule here because I'm coming in greater than 0. I'll plug in 0, and I get a 0 plus 2, which is 2. Right? When you do a direct substitution here, you get 0 plus 2, and that equals 2, and so we're going to circle letter A there. On number 10, I'm coming at 2 from the positive side. So again, I want to use the rule for numbers that are greater than 2. So I'm going to have negative 2 minus 4 with direct substitution, which is negative 6. That's letter B. So all of these problems are simply direct substitution. We just have to be careful and choose the correct rule. Sometimes it's the top rule, sometimes it's the bottom rule. Pay attention to which side of the which limit you're doing, the left side or the right side limit, left hand or right hand limit. Okay, 1 through 10 shouldn't feel too bad. Let's see what's next. In 11 through 14, the limits involve infinity. We're sending x to either positive or negative infinity. And so for most of these, we're simply going to use that chart that we had. Let me remind you, when the top has a bigger degree, that's the most complicated one. That's some form of infinity or does not exist. When the degrees are the same, we do the ratio of the leading coefficients. So we do the fraction. And when the degree on bottom is big, let's just say big bottom, that limit goes to 0. Okay, that is a terrible summary of the chart we had in class, but those are the rules I'm going to follow as I attack these limits. So right out of the gate, I look at this expression here in number 11, and I notice that the degree on top is 1, the degree on bottom is 2, the degree on bottom is bigger, this thing is going to 0. So I'm going to choose letter B. Right out of the gate, that one goes to 0. Okay, in problem 12, these are both linear. And so what I'm going to do is the ratio of the coefficients, the leading coefficients. So this is a 2 over 1, which is 2. I'm going to choose letter A. For number 13, again, two polynomials. The degree of the leading coefficients is the same, or the leading term of the degree is the same. So degree 2 on top, degree 2 on bottom. My leading coefficients are 3 over 1, so I'm going to choose A on this one as well. And on number 14, again, two linear terms, the degree is the same. So this is a 2 over 1, and I'm going to choose letter C. So nothing out of the ordinary on these four problems. I didn't even have to use some number over 0 to try and figure out if I was going to positive, negative, infinity, or does not exist. In 11 through 14, you use the rules. If they're equal, make the fraction. If the bottom's bigger, it goes to 0. So far, so good. Okay, let's move on. The last four problems are just about intervals where functions are continuous. So we have to examine each function individually to find out what's going on. Right away on number 15, we get a polynomial. And we happen to know that polynomials are continuous on all the real numbers. So I just have to pick out the interval that includes all the real numbers. And we've studied interval notation enough to know that this interval here, open interval, negative infinity to infinity, that's the same as all real numbers. So I'm choosing letter C on this one because for polynomials, we know they're continuous everywhere. For piecewise functions, we're not sure if they're continuous everywhere. The first thing we need to do is we need to check out these individual expressions. So for numbers less than 1, I'm following the linear equation negative 2x plus 5. That is continuous because it's a polynomial, a linear equation. On the bottom, I'm doing the parabola negative x squared plus 4x minus 4. That guy is continuous. So the only place where this might be discontinuous is at that transition point, x equals 1. And so we're going to test both functions at x equals 1 to decide what's happening. When I plug 1 in on top, I get negative 2 plus 5, which is 3. When I plug 1 in on bottom, I get negative 1 plus 4 minus 4, which is negative 1. These numbers are different. So 1 is a discontinuity, meaning it's thrown out of the function. And unfortunately, now that I look at these answers, letter C is supposed to be the right answer. This bracket, though, should be a curved parentheses. So I apologize for that on our practice test. 1 is not included in this continuity expression. This thing is discontinuous at 1 because there's a jump. It's clearly a jump. We're at 3 and negative 1. So the interval would be negative infinity to 1 and 1 to infinity. Those are the places where it's continuous. Okay, let's take a look at 17. 17 again is piecewise. The linear terms are continuous. The linear expressions are continuous. So the only interesting point is 0. If I plug 0 in on top, I get 0 minus 1, which is negative 1. If I plug 0 in on bottom, I get 0 plus 3. That means there's a jump there. This is discontinuous. It's discontinuous at 0. And again, I'm gonna make this correction here. The function is continuous everywhere but 0. So I would write that as negative infinity to 0 union 0 to infinity. When we do our actual test, I'm going to correct the way these notations are written. So we'll fix that. But this one, we're going to say A because 0 is the point of discontinuity. So A is the answer on that. And then for number 18, for this function, this is a rational function, and so we want to look for places where the denominator equals 0. So literally, 2x plus 4 equals 0. We solve this, and we end up with x equals negative 2. And that's the point that's going to get thrown out, and sure enough, letter D fits the bill. Okay? So we are discontinuous at 2. We're continuous everywhere else, and so we're choosing letter D there. This is the end of the multiple choice section, and the test that you take is going to be very similar. We'll run through the substitution limits. We'll do a couple where you have to do algebra. We'll do the limits as x goes to infinity. These are the continuity questions. And then we get to the free response, and that's next. The free response questions will be similar to the ones that we're practicing. So the first question is going to be a sandwich theorem problem. I know it doesn't say sandwich theorem on this problem, but I can tell by the way it's stated that my only chance is the sandwich theorem. I'm given this compound inequality, and notice function f is trapped in between two other functions, right? F is in the middle, and it's between 3x minus 2 and x cubed. Then later in the reading, the statement of the problem, they're telling me the interval for x, so x is somewhere between 0 and 2, and then they're asking us to find the limit as x approaches 1 of f of x. There is no chance for me to do what I like to do, which is substitution, because I don't have an expression for f of x. What I do have are two other expressions for functions that trap my function. So here's the strategy for problems like this. Any kind of sandwich theorem. You have the functions that do the trapping, so we're going to compute each limit. So step 1, f of, let's do limit. Limit as x approaches 1, because I want to use the same value there. Limit as x approaches 1 of 3x minus 2. When you plug in 1, you get 1. So that limit is 1. That's good news. Number 2, limit as x approaches 1 of x cubed, which is the other end. You plug in 1, that guy equals 1. And because both of these limits equal 1 and our function is trapped, we can apply the sandwich theorem. Okay, so now we want to write out a sentence, a complete explanation, stating why we've achieved the limit. All right. So, given 3x minus 2 is less than or equal to f of x is less than or equal to x cubed, and knowing the limit as x approaches 1 of 3x minus 2 equals the limit as x approaches 1 of x cubed equals 1, knowing that those two limits are the same and they equal 1, and then you have to say the sandwich theorem. So I usually put by the sandwich theorem because I fulfilled the hypothesis. I put this in red because I want to make sure you write this in your answer. By the sandwich theorem, Theorem, the limit as x approaches 1 on our function f of x has to also equal 1. Take that, universe. We set up the hypothesis for the sandwich theorem, which is we need to make sure we have our function trapped, and we need to know that the limits on the outside functions are equal. If we have that in place, then we can say, by the sandwich theorem, here's the limit. So when you're writing your answer to this problem, I'm going to look for three things. I'm going to look for, did they do the math, the limit on the left-hand function? Did they do the limit on the right-hand function? And then did they write a sentence where they stated what they did and they said by the sandwich theorem? And then, of course, I need to know what the answer to the limit is. Remember, the limit here is 1. Oops, that's not good. The limit here is 1, all right? Our limit is 1. I'm just going to put it in blue there so you can see it. So do the limit on the bounding functions. Write a note saying that you had the setup. Make sure you say I'm applying the sandwich theorem, and then tell me the answer. The limit equals 1 is the answer. These problems aren't bad. This is just a basic introductory sandwich theorem question. I am not trying to ruin your life. I'm trying to get you used to speaking the language. Okay, let's see what's next on the free response section. The other named theorem that we studied in this section was the intermediate value theorem. And we call that the IVT. Okay, the reason I know that the IVT applies here is all of the problems that we've been practicing that apply this theorem show that a function has at least one zero on a closed interval. And then we're going to include an explanation. So we're going to apply the intermediate value theorem. We're going to mention it in our explanation. Okay. So first of all, we need a function on a closed interval, a continuous function on a closed interval. So I'm going to say something like since. Now maybe I shouldn't write in cursive. That says since f of x is continuous on 0, 2. And that's true because this function, the point of discontinuity is at 8, and 8 is not in 0, 2. So since f of x is continuous on 0, 2, and f of 0 equals whatever f of 0 is. So let's do the math on that. You have to know the cosine of 0. The cosine of 0 happens to be 1. So this is 0 minus 1 up there. So it's going to be 24 times 0 squared, which is 0, minus cosine of 0, which is 1, over negative 8. So this is negative 24 divided by negative 8, which is negative 3. So since f of x is continuous on 0, 2, and f of 0 is negative 3, and f of 2 is going to be 24 times 4 minus cosine of 2 pi over 4 is the same as cosine of pi over 2. That's 0, so 4 minus 0 over, and then 2 minus 8 is negative 6. So this is going to be negative 4 times 4, which is negative 16. And right now, you're probably screaming at the video saying, Mr. Murphy, you screwed up on this problem. This is not negative 3. Do you see it? Negative 24 divided by negative 8 is positive 3. So I'm going to try and use my eraser and see if that works. Well, it took the white away, but apparently I don't know how to use this thing. So here's what I'm going to do. I'm going to go old school, cross out that, and make this a 3. Okay, since f of x is continuous on 0, 2, and f of 0 is 3, and f of 2 is negative 16, there exists c in 0, 2. This is such that f of c equals 0 by the intermediate value theorem. Okay? So when I'm grading these problems, I look for basically 3 things, maybe 4. So I look for the fact that you verify we're continuous on a closed interval. Okay, that's good news. I look for the values at the endpoints, so f of 0 and f of 2. One of them's got to be positive, one of them's got to be negative. And then I look for you to make the statement that the value exists by the intermediate value theorem. And you can use IVT in your written story. But I got to see that you verified it was continuous on the closed interval. I'm going to look for, did you compute the 2 values? And is one below your line and one above your line? In this case, we're trying to find zeros, right? Because it says find the zeros of the function, at least 1 0. And then you have to mention IVT somewhere. Got to have IVT written in there. Intermediate value theorem. No exceptions in terms of me giving full credit on this thing. Okay, hopefully you'll write a little more coherently than I did, but you get the gist of this thing. Let's wrap this up. Our last couple of free response problems are limits involving trig functions. And so let me just, without too much fanfare, run through and compute these limits. So we have already discussed a lot how to attack these limits. We want to have the sine of the house over the house. So in this case, I have sine of 6x. I need 6x on the bottom, and right now I have 3x. So I'm going to multiply by a form of 1, which is 2 over 2, so I can force the 6x on the bottom. This limit turns into 2 sine of 6x, 6x over 6x. And then we split it into 2 limits, or factor the 2 out, however you want to do that. But it's 2 times the limit as x approaches 0 of sine of 6x over 6x. And we've already discussed how, as long as x is going to 0, 6x is going to 0. And so this limit here, this thing here, is a 1. And so this is just 2 times 1, which is 2. And 2 is the answer on this limit. That's the y value that the fingers are pointing toward. Let me draw a little dividing line here, and then we'll do number 22. For this one, because we have a fraction with a binomial in the numerator and a single term in the denominator, I'm going to recommend that we split this into two pieces. So this is going to be the limit as x approaches 0 of 6x over 2x minus the limit as x approaches 0 of sine 9x over 2x. And then let's just work on this left side real quick. The x's are going to cancel, and this limit is just 3. 6 over 2 is 3. So I've got this one done. On this side, I need to do a little manipulation here. I want 9x underneath the sine of x. And you can decide exactly how I want to attack that. I'm actually going to go ahead and just put a 9x in, so I don't even have to think about how to get a 2 turning into a 9x. So I'm going to put 9x here. If I do that, I got to multiply by it on top. And then we've got the sine of 9x. Oops, goodness. Let's try that again. The sine of 9x. And then it won't take much to see that this guy is a 1, right? And this one is a 9 over 2. Oh, don't forget that x is going to 0. So essentially what we have is 3 minus 9 over 2. So that's 6 over 2 minus 9 over 2, which is negative 3 over 2. Now I want to mention that I really did kind of a faux pas here. Any limit that you attack, you should always try substitution first. So I didn't do that, but let's go back and on the flip side here, we'll double check this. When you plug in 0 for x on the number 21 directly, you get the sine of 0 over 0. The sine of 0 is 0, and then obviously 0 is 0. So that one is an indeterminate form. That's what allows us to do our little trick. Same thing over here. This one's going to be 0 minus 0 over 0, which is also 0 over 0, so that's a good move. So try substitution first. I'm not going to intend to trick you, but that is a great practice to get in the habit of doing. Try substitution first. If you get an indeterminate form, then you get to do all the fun math. All right? And essentially that's our test on limits. We're just trying to hit the highlights of the things that we've covered over the last couple weeks and demonstrate that we've got a handle on it so we can move on to our derivatives soon. Okay? So good luck studying. We'll talk more about this soon. Don't panic. I think it's going to go great for you. Take care.